there's an important subset of properties which apply to solutions called colligative properties. These are kind of interesting in that they only depend on the number of particles that we dissolve in the solution, and not necessarily the identity of the particles. So when we look up constants for these solutions, we'll always look them up for the solvent. We won't worry about whether we're mixing in sugar, whether we're mixing in salt, as long as we count how many pieces we wind up with in the solution, how many ions and molecules, then we'll be able to calculate whatever our colligative property is. Now there's a caveat, which is that these only truly apply to ideal solutions. And so they give us approximate results, even if we don't have an ideal solution. But we're going to want to be very mindful about how close we are to the ideal case in order to interpret how good of an answer we're getting from our colligative property calculations. To understand what an ideal solution is, let's compare it to something we already have good intuition for, which is an ideal gas. So ideal gas, it doesn't matter what the identity of the gases are that we have in our container. We can just calculate the number of moles of gas we have and stick it into our ideal gas equation and get the pressure. The reason we can do that is because these gases we're stipulating are under conditions in which intermolecular forces are very weak or very negligible. So if we have two different molecules come into contact with each other, they'll strike each other and bounce off without having any significant attraction. They don't clump together, they don't slow down, we don't reduce their kinetic energy. And so they are free to make their way to the walls of the container relatively unhindered, bounce off the walls, and exert a pressure. And that pressure is not going to be reduced by intermolecular forces. Now, an ideal solution, we definitely have strong intermolecular forces. That's what's holding all these molecules together in the liquid phase. But if we set up certain conditions, if we say that, well, the blue molecules here have to have comparable intermolecular forces to the green molecules, have to have comparable intermolecular forces to the blue molecules interacting with the green molecules, then motion throughout this solution is going to be unhindered. The intermolecular forces are still going to keep these molecules from spontaneously exploring the walls of their container as a gas, but they're not going to prevent these green molecules from swapping places with the blue molecules and diffusing throughout the confines of the solution. So it's a different kind of motion, but just like in the ideal gas case, the intermolecular forces are not going to hinder the dispersion of the molecules. Something else that would make our ideal gas approximation a good one is when we have a low pressure gas with very few gas molecules colliding with each other in our container. So in that case, even if there were very strong interactions between the molecules, it's unlikely they're ever going to interact with each other, so it doesn't really matter. What that means is that for any gas, if it's low enough pressure, an ideal gas approximation is going to be pretty good, and all gases are going to behave as ideal gases at zero pressure, since then they're not going to have any intermolecular collisions. For an ideal solution, the similar idea is that we want to have low concentration. So we have few solute-solute interactions. Now what about solute-solvent interactions? Well, even if we had very strong solute-solvent interactions, what that would mean is that this solute molecule would essentially just pick up a cluster of solvent molecules around it, but we'd still have just one particle then moving through the solution. We wouldn't have a large effect on the majority of the molecules in the solution. And if we have a dilute enough solution, these solute particles are never going to interact with each other. So their self-interactions is not going to contribute to the way the solution behaves. So we will always have an ideal solution if we're at infinite dilution, with essentially just one molecule dissolved in our solution. A very important colligative property which tells us about vapor pressure is described by Raoult's law. Now, to understand Raoult's law, imagine that we have over here our pure solvent. So a certain number of these liquid molecules are escaping into the vapor phase. A certain number of the vapor molecules are condensing in the liquid phase. And if we close our container and wait, we'll eventually reach equilibrium, where the same number are moving out of the liquid phase and out of the gas phase. Well, what would happen if we blocked some of these sites from evaporating, but we had the same number of sites for condensation. I think it stands to reason that we're going to reduce the number of evaporated gas molecules. So the way we do that, we add a solute with these green molecules here. And a solute definitely has intermolecular attractions to these solvent molecules. And so the gas molecules are still going to be able to condense if they strike one of our solute molecules. They'll still have some attraction and they can adhere to them and become part of the solution again. But I think it's pretty clear that if the blue molecules want to evaporate, they can't do so with this molecule standing in the way. So we reduce the number of evaporations, but the number of condensations is unchanged. The overall effect is that the number of molecules in the gas phase is going to decrease. In this case, since we blocked a third of those evaporation sites, we are also going to reduce the number of evaporated molecules by a third and have 2/3 the pressure. We can write this in equation form. So what we are saying is that the pressure of our vapor is going to be equal to the pressure that it would be for an ideal solution. That's what this circle means. It means it's our ideal solution under standard conditions. But it's only going to be a fraction of that, corresponding to the fraction of our solvent in the solution. So in this case, we had a fraction of 2/3. So our vapor pressure wound up being 2/3 what it would have been otherwise in the pure case. And so that's our mole fraction. Now, say we let these green molecules go ahead and escape as well. And Raoult's law will also describe that situation. So we can use Raoult's law to figure out the vapor pressure for the blue molecules, and we can use Raoult's law to figure out the vapor pressure from the green molecules. And altogether, that will be the total pressure in our container. Let's say we have a solution. Our solution consists of ethanol and methanol, 3 moles of ethanol, 5 moles of methanol. We're at 20 degrees Celsius. What's going to be the pressure exerted over the solvents if we have a closed container due to their evaporation? Well, the first thing we need to do is we need to look up the pressures for these. And if we find pressures, these must be volatile substances. They're both going to contribute to that overall pressure. We look these up at 20 degrees Celsius. For methanol, it's 97.3 millimeters of mercury. For ethanol, it's 43.7 millimeters of mercury. Now we can apply Raoult's law by calculating the mole fraction and multiplying that by the pressure that we would have in the pure case. So for methanol, we have 5 moles of methanol, and that's added to 3 moles of ethanol. So 5 over 8 times the 97.3 that we would have if it was pure methanol, and we get a vapor pressure of 60.8 millimeters of mercury. We can do the same thing for ethanol, since it's also volatile. In this case, it's 3 moles of ethanol over our total 8 moles times the 43.7. We get 16.4 millimeters of mercury. Now, if we add those together to get our total pressure, remember Dalton's law of partial pressures, the total pressure is just equal to the sum of the pressures of the individual gases, then that comes out to 77.2 millimeters of mercury, about 1/10 of an atmosphere. Another colligative property is freezing point depression. This is where the freezing point of our solution tends to go down as we add more solute to it. Let's consider the case where we haven't added any solutes. We just have our pure solvent. Solvent molecules are all tumbling over each other in different directions, and this has many microstates. Anytime a molecule is moving this way versus that way versus this way versus that way, those are all different microstates, so clearly there's a lot of configurations for our system. Compare that to the solid case. If we have all the molecules kind of locked together in a crystal, they aren't really moving around, let's say that that corresponds to about just 1 microstate. Just not very many ways to arrange the molecules in that system. Well, that is a significant difference in entropy. We have all these arrangements, and we go down to just 1 arrangement. We have decreased entropy. We don't like to do that, so we're going to have to pay a price for it. We're going to pay that price in energy. we're going to have to suck out a certain amount of energy in order to get between the first case and the second case. That's going to be our change in temperature for the system. Or we're going to have to buy a freezer, and we're going to have to pay money to the electric company in order to, whatever amount of electricity we need in order to run the pump and get this change in temperature. So there's a literal physical price associated with wanting to suck out this energy and violate entropy. Let's consider the case where we have a solute added. So say we've added some salt to this solution. So at the salt particles, now if we consider the liquid case, these can flip positions with any of those solvent particles. There's going to be a lot more microstates now. Every time we flip one of these, we have a whole new set of microstates. So it's much more disordered than in the case without the solute. Well, what about the solid case? Well, in the solid case, we're going to form still a nice crystal of our solvent particles and probably push these solute particles out to the edge. And still, these aren't moving around in any direction. So really, there's still basically about one way to configure the system. We have about on the order of one microstate. So the disorder between the solid states hasn't changed, but the disorder between the liquid states has. It's much more disordered here. Well, since we go from a much more disordered state to that ordered state, we're going to have a bigger entropy decrease. And so we're going to have to pay a bigger price for that decrease in energy. So we're going to need a larger difference in temperature in order to transition to the solid state. We're going to have to pay a more expensive electric bill in order to run this freezer. Representing freezing point depression mathematically is actually fairly straightforward. It's going to be the case for all of our colligative properties. Since we don't have to model any of the solute-solute interactions or solute-solvent interactions, all we have to do is take the number of particles and multiply that by the amount change per particle. And that should always be the same since they're not interacting with each other and having any complex effects. So the way we're going to write the number of particles, usually we count that in concentration. Now, ordinarily, concentration is measured in molarity, moles per unit volume. That's actually a very bad form of measurement to use during freezing point depression because we are changing the temperature, and what varies with temperature? Volume. So our concentration would be changing over the course of our experiment, which is not what we want. So instead, we're going to modify our definition a little bit. We're going to use what's called molality. Essentially the same as molarity, except for instead of being moles over liters of solution, it's going to be moles over kilograms of solvent. Now what happens if we have something like NaCl and it breaks apart into sodiums and chlorines? We're going to have twice as many particles in our solution as we did NaCl's that we counted. So to fix that, we include a factor here, the Van Hoff factor. That's just the number of pieces the solute particles produce. So if we have NaCl produces 2 ions, then we would put a factor of 2 here. So we can double our amount of particles that we're accounting for. Now the amount of change per particle is just our freezing point constant. And since this is a colligative property, this depends only on the solvent. So we'll have to look up that freezing point constant for our particular solvent. And once we calculate the change in freezing point, the last step is to go ahead and consider what our original freezing point was that we changed. So our new freezing point is going to be equal to our old freezing point for our pure solution minus the change in temperature that we calculated for our depression. Let's say that we go ahead and add 90 grams of sodium chloride to 1.5 liters of water. How is that going to affect the freezing point? First thing we're going to need to do to use our freezing point depression equation, we're going to need to start finding some of these constants. So if we look up the freezing point constant, Kf for water, we'll find that that's 1.86 degrees Celsius per molal. A molal is a unit of molality. Those units of moles of solute over kilograms of solvent that we're going to use instead of molarity for these problems. Note the Van Hoff factor here, as mentioned, since sodium chloride splits into sodium plus and chlorine minus, we actually have 2 particles for every 1 particle that we measured. And so our Van Hoff factor is going to be equal to 2. Now our molality, we'll go ahead and plug in. So we had 90 kilograms of NaCl, which weighs 58.44 grams for every 1 mole. So that will get us into moles of NaCl. And a liter of water weighs about 1 kilogram. So we'll call this 1.5 kilograms of H2O. And this comes out to 1.027 molals as our molality. Now we have all the constants we need to go ahead and plug into our expression. So Van Hoff was 2, molality was 1.027, our freezing point depression constant, 1.86 degrees Celsius per molal. And the molalities cancel, so we get units of Celsius. Our total change is 3.82 degrees Celsius. Now don't forget the final step here, which is that now we need to apply that change to our original temperature. Now for water, water freezes at 0 degrees Celsius. So we'll take that 0 degrees Celsius and subtract our freezing point depression. And our answer is that now our water is going to freeze at minus 3.82 degrees Celsius. So this is why we salt the roads whenever winter comes along. That decreases the temperature at which the water is going to freeze. And so if it gets down to near 0, but it doesn't get too far below 0, then this salting process that we came up with is going to be enough to keep the solution in the liquid phase and not cause the roads to ice over. We can apply similar reasoning to what happens to the boiling point of a liquid when we include solute particles in our solution. Now, if we don't have any solute particles, we just have a pure solvent, and we convert it into the gas phase by heating. Then those gas molecules can explore the confines of the container. They can bounce around in all sorts of different directions. This is our high entropy case. We have a very big increase in entropy going from the liquid to the gas phase. Well, since that's favorable, we don't have to pay quite the same price to make it happen. This is going to lower our energy cost. In fact, if we didn't heat our solution at all, if we just waited and left the container open, it would all convert into gas on its own, because that's favored by entropy. What if we added a salt here? Well, now we have a much more disordered solution phase. We have all sorts of different arrangements where we can swap these solute and solvent molecules. When we get to the gas phase, however, there's not really a distinction. The solute molecules are all going to be deposited on the container if they're not volatile. And so we aren't going to have gained anything in that case. So effectively, we have decreased the favorability here. Instead of going from a low entropy case to a high entropy case, we've gone from a moderate entropy case to a high entropy case. You could also think of this in terms of decreasing the entropy of these solute particles. Right now they have a nice high entropy. They can explore all around in the solution. But now we've taken them and we've organized them into a state where they only have one possible configuration. So since we organize them, we have to pay a price for that. And price is going to be our increase in energy cost. So it's going to take more energy in order to boil the solution with these solute particles versus one that doesn't have them, which means we're going to need a bigger change in temperature. We likewise have a very similar equation for our boiling point change, since we use the same reasoning that we used for our freezing point change. So we just have to take the number of particles in our solution, which is the concentration times however many ions are generated, and we multiply that by the amount change per particle. Once we do that, then to calculate the new boiling point, we take our original boiling point and add the change in boiling point. And all the calculations proceed the same way that they did for our freezing point depression. The final colligative property we're going to consider is what's called osmotic pressure. This is defined to be the pressure that you have to apply in order to prevent solvent from moving across a membrane. Our membrane is going to be this semi-permeable membrane. It means it's going to let the solvent molecules move back and forth, but it's not going to let the solute particles cross. They're going to be stuck on whatever side they happen to be on. Now the question is, where would these solvent particles prefer to be? Would they prefer to be on the left side or the right side? I'm going to answer this question in two ways. One way we can answer this question is by thinking of it in terms of entropy. If you're a solvent molecule over here on the left side, and you swap places with any of these other molecules, it doesn't really affect the look of the system. So that's not very many microstates. However, if you move over to this other side, you can swap places with this green molecule or this green molecule or this green molecule or this green molecule, and those would all correspond to different microstates. So there's a lot more entropy if you move over here compared to if you stay over here. Because we always like to increase in entropy, that means that in general, our solvent molecules are going to want to move over to the right side. That motion, that preference, is going to create a pressure. Another way you can think of this is think about our solution where we had a vapor over it, and the solution had a bunch of solute particles mixed in. So these solute particles, they would prevent the solvent from evaporating, but they would not prevent the vapor from condensing. Similar situation here because of our semi-permeable membrane. All of these molecules on the left side can move over to the right side. So they're all pushing effectively towards the right side. These molecules on the left side, wherever there's a green molecule, that's going to be blocking any motion going the other direction. So the presence of these molecules is going to reduce the total amount of pushing that can happen in this other direction. And so that's going to decrease the ratio of molecules moving this way versus that way. And so we'll have a net flux this way, which we can correlate to a pressure in this direction. A way to visualize this osmotic pressure, we can add a liquid to this U-shaped tubing with a semi-permeable membrane exactly in the middle. Now let's say that we add some solute to one side. Well, we know that's going to decrease the osmotic pressure on that side. It's going to block the flow of molecules this way, but the molecules this way will be unimpeded. So overall, we'll have a higher flow going to the right, and we'll wind up with more solution on the right side. But what happens during this process is that we start to increase in height over here, our solution. Gravity is going to be pushing back down. Eventually, we're going to have enough force from gravity to counteract the pressure of the molecules moving this direction. And so we'll come to an equilibrium, with one side a little bit more elevated than the other side. So if we were to take the weight of this side and divide it by the cross-sectional area of the tube, that would be the force per unit area. It would be the osmotic pressure of this tube. Now, just like with our other colligative properties, we can write an equation to represent them. Our equation is going to be the number of particles times the amount per particle. In this case, the pressure per particle. So our number of particles is going to be the Van 't Hoff factor times, in this case, we're going to go back to using molarity. So we're now at the same temperature throughout our experiment, most likely. So we can use units of molarity. That's all right. Then we'll have the gas constant and the temperature. We use the Greek letter pi to represent the osmotic pressure because we don't want to confuse it with our gas pressure. Now this equation actually looks pretty familiar. Remember, molarity is moles per unit volume. So we can think of that as N over V. And if we make that substitution into this equation, then we have that our pressure is equal to the number of moles times the real gas constant, the ideal gas constant, times the temperature, divided by the volume. So this actually has the same form as PV equals nRT, which goes to show you how tightly related ideal gases are to ideal solutions.